Hello and welcome back to another episode of Math with Son. Today we're continuing conservation of energy, and we're going to do a few random examples, some with a spring and another one with a loop-de-loop. All right, so we got this first one with the spring, which is really going to be a bow and arrow. Hawkeye uses a force of 100 newtons to pull a 0.2 kilogram arrow a distance of 0.15 meters against a bowstring. What is the bow's constant force? So what is the spring constant essentially? So the spring constant is equal to Kx. And if that's the case, if we know that Hawkeye had a force of 100 newtons and he pulled at a distance of 0.2, you could do 100 is equal to K times 0.2. And if you divide... I can't read. A distance of 0.15. 0.15. If you pull it back, 0.15, and if we divide by 0.15, we get 100 divided by 0.15 is essentially 667 newtons meters for that spring constant. Okay? So what would be the velocity that the arrow will be propelled when it leaves the bow? This is where conservation of energy is going to come into play. So remember that your potential energy and your kinetic energy initial must be equal to your potential final and your kinetic energy final. So let's think about what we have going on here. Is there any kinetic energy in the very beginning? No. We have pulled this bow back, bow and arrow, on the string. We have pulled the arrow back, and it is not moved yet, so there's no kinetic energy in the beginning. We do have a whole bunch of potential energy, and we do have a whole bunch of kinetic energy at the end. We don't have any kinetic energy at the end, potential energy at the end, because the potential energy, once we've released this arrow, is gone. It is gone, and it is no longer going to have potential energy at the end. So we really know that our potential in the beginning must equal our kinetic final. All right, so let's do some things here. We got our potential in the beginning, which is going to be 1/2 kx squared. That would be the force with that spring, must be equal to the kinetic. The potential in the beginning must be equal to the kinetic at the end. I'm all thumbs today with my voice. Would be 1/2 mv squared. Well, look what's going to cancel. These look almost the same, and there's a reason for that, because they're both very similar. The 1/2s cancel. We know our k, we know our x squared, but we're looking for the final velocity, so let's just solve for v before we do any of that. Let's divide by m and square root. You'd get kx squared over m. The square root of that would equal your v for your final. All right, now we can plug everything in. We got k is 667. We got x. What's x? That would be 0.15. Let's not mess that up. Squared all over a mass of 0.2. And if you square root all that and you do all the math, you figure out that this is going to be 8.7 meters per second for that final velocity.